In this video, we will talk about functions. So, what is a function? Let's say we have a set x and a set y, such that we have an x in x and a y in y. Then a function is going to be a relation that for every x in x there is a unique, so for every x in x there is a unique y in y. So what we mean by unique, we mean that there is only one of these y's to which the x is mapped, and this is written in the form, so the function is written like this: x y. So this is x mapping into y. So for every element that I will pick x in the set x, it should be mapped only to one element in y. Then that is a function. So every element in y, so everything, nothing should be left out in x. I mean, in x should be mapped to a unique element, to one element in y. Now let us identify some of these questions. So we have these examples here. So let us identify which one is a function and which one is not a function. Now, from the definition that we've said, for all x here, for every x, there must be a unique y in the set y. So for the set A, we see that every element in x is mapped to only one. So here B, we see that C is mapped to x and B is mapped to x. So B is mapped to x. That's only one element which it's mapped to. And C is also mapped to x. That's only one element. A is mapped to Z and D is mapped to W. So we see that all the elements in x are mapped to one element in y. So this here is a function. So now let us look at B. So when it comes to B, we see that A is mapped to Z, B is mapped to X, but again B is mapped to Y. Then we have C to W and D goes to X. So this is not a function because B is mapped to two different elements, which is X and Y. And from the definition, we say that B must be mapped only to one element, to a unique element, which is supposed to be 1. So it should have only been mapped to x or y. So this is disqualified from being a function. So this is not a function. So if this is not a function, let us look at this other one. So is this a function? So this one is also a function because it is mapped only to every element in x is mapped only to one element in y. So this is a function. So this other one here, D. So D is not a function because not every element in the set x is mapped to an element in y. So everything here should have been mapped to something in y. So this disqualifies from being a function. So this is not a function. Okay, so how then do we move on? So we have this question, this other question here. So this question, we see that every element here that we have in x, A, B, C, and D, is mapped to a unique element or to one element in what? In the set y, which is z. So this is a function. This is a function. So now, for the function, The unique elements which they are being mapped to, which are the ones we're saying y in the set y, are the unique elements which are being related to the ones x in x. So these y's, y in y, these are called the image of what? It's called the image of x. So the y is called the image of x and is written or denoted as f of x, like that. Then we have that the set of the image. So the set of all these y's, the set of the y's, set of the y's is called the range. The set of the image or set of the y's is called the range. Then the set of, so the set of x, set of the x, the whole entire x, that is the domain. That is called the domain. Okay, so now from here, let us look at a question. So we have this question. It says let r, okay, it says let f such that r is being mapped into r be a function which relates to each real number and its square. So this should be a function that relates each real number and its square. So this can be written in form of an equation. So that would be f of x is equal to x squared, which means for every real number I will put in this, I can relate it, then so it's saying to its square, so meaning every real number is going to be squared. So this is the equation that represents this function. So not only can this equation be represented like this, but we can write it in set Peter notation to say for every x, so the x is representing a real number there, then the second point that we'll be getting, that will be, or the image that we'll be having, is going to be the square of that real number, such that I have x a member of real numbers, like that. Now this here we can graph this. We can graph this equation. So how can we graph it like this? So this equation will appear to be in this form, which is y is equal to x squared. So y is equal to x squared. So this is the function that represents, or this is how that function is represented on the graph. Then the domain of the function r and its, so the domain, the domain of this function is r, or is the set of real numbers. The set of real numbers, which can be represented also in interval form as -2, like that. So meaning for every real number I will get, it be -1, it be 1, 2, 3, when I get and square it, so I can get that this function will still be defined when I place in any real number. So now what will be my range? So my range is what I'll be getting back. My range, so this is my domain. My range is what I'll be getting when I place my real numbers in that function. So I see that I get only positive numbers, only positive numbers. So it starts from 0 going all the way to positive infinity. That's what I will be getting when I place my real numbers there. So this is my range. Now, okay, now let us look at another concept. So let us look at the concept of a function being one-to-one. So if I have a function f such that x is being mapped to y, so this function is said to be one-to-one. It's said to be one-to-one if for every x there is only one distinct corresponding what image in y. There is only one element that is corresponding to that other element in what in y, and this can be written as f of x1 like this. It's equal to f of x2 equal to x1 equal to x2. So let's look at an example. An example can be if we have this arrow diagram like this, where this is my x and I have another one that is denoting my y like that. So if I have x1, x2, x3, x4, I have y1, y2, y3, y4 like that. Then these x's must correspond only to one y in this y. So if I have my x2 going there to my x1, then I have my x1 going to my x3, and then I have my x3 going to my x4, then I have my x4 going to my x2 there. So we see that these x's are mapped to only one distinct. So this x cannot go to to many of these. It should be only one for it to be a function. It should only be one. It should only be one and not many others. It should only be one and not let's say these x1, x2, x3, x4. Maybe if it was x1 going to one point and that one again x2 going to the same point, then it would not be one to one, but it's one to one since it is going to only one distinct point. So this is how we denote to say that a function is one to one. So another example can be if we have, so let us have the function f of x is equal to root of x. So if we have this function and we are told to prove that this function is one to one, so we say let x1, x2 be a member of the real numbers, and this is being defined. It's a function such that it's mapping real numbers onto real numbers like that. So if we have such an equation to show this, to show that this function is one to one, we will say let x1, x2 be a member of the real numbers. Then we have f x1 should be equal to f x2. This is what we're trying to show. This is what we're trying to show, that this is going to be equal. So how do we do this? We square both sides of the function. So the function is like this. It's defined like that. x2. So we square this side and then I square the other side. Then the square goes. So when the square goes, I just have x1 equal to x2. So this shows hence that this is a one-to-one function. It's a one-to-one function. Okay, since this has been satisfied, we have the function equal to be x1 x2, and when I replace this function and I square both sides, I'll get x1 equal to x2. So this has been satisfied. Now let us look at another example where we do not have a one-to-one function. So if we have the function, so saying we have, talking of real numbers still, okay, then I have the function f of x being equal to x squared. So for this one, this will not give me a one-to-one function. Okay, let's see this. So let you say the same, let x1, x2 be a member of the real numbers. Then from here, if I say f of x1 must be equal to f of x2, which should be equal to x1 should be equal to x2. So now I must show, so this here we see it's defined by the squared, so these are squared like that. Now to continue with this implies if I get the root there, I'll have x1 being equal to plus minus root of x like that, x2 squared like that. So now from here I'll just have this is going to be equal to plus minus x2. Then from there I see that I have two values. I have that x1 is equal to positive x2, and again x1 is equal to x negative x2. So this is not a one-to-one function, since x is being mapped onto two different elements, but we are saying that it should only be mapped onto a distinct element. So it should have been mapped maybe only onto x2 or negative x2, but since it's mapped onto both, it is not one to one. So we can even see this from the sketch of the graph. So the sketch of this graph, f of x equal to x squared, is okay. This is the sketch. So the sketch is like that. So from here I see that when I have that point like that up to there, if this is my f of x1 saying equal to f of x2, like that. So at the same point, when I touch the graph, when I reach that side, this gives me a positive value, that there gives me a negative value. So this is not a one-to-one function. This is not a one-to-one function. So on the previous graph, there was an error. So the previous graph was supposed to look something like this. Yeah, that was the previous graph for the root of x. That's the previous graph. So you can represent that in that manner. So you can represent that like that. Okay, that's for x root of x squared. That's that graph. Okay, now let us proceed. So we'll proceed to understanding another one, which is many to one. Many to one. When do we call a function to be many to one? So a function is said to be, the function f such that x is mapped to y is said to be many to one when I have, so an example, I have x, so x1, x2, and x3, and then I have y like this, such that, so if this is my f, x1 will be equal to f of x2, like that, then I have f of x2. So if I have x1 mapped to this here and that one mapped like that, so this will be equal, like f of x1 is equal to f of x2, since they are being mapped to the same point, and I have this one mapped there, x3 to that point there. So this then shows me that this is a many to one, since many of these points are mapping only to one there. So this is a many to one function. Many to one function. Now, when do we have another concept where we say an onto function? An onto function. So we have these diagrams here. So for a function f of x like that, for a function I mean f such that x is mapped to y. So for this, where we say that it is onto, so we say that this function is onto if for every y in y, for every, meaning everything, every element in y, for every element in y, for this image, because we said y is the image that is being formed, there is some x in x, there's a corresponding x in x. So this is we are saying, yeah, there must exist an x in x. For every y in y, there must exist an x in x. So then this will be what? Will be onto. So we can see that in the first one it is onto, because for every y here, the x, y, and z, there's a corresponding what's this element, which is a, b, c, and d. So this is onto. Then for this one, we only have the element, we only have a member z there. So if we have z there in this set x, we have that just z. So z has a corresponding what's this element in y, which are these here. They are corresponding elements. So this is also onto. Now for the last one, it is not onto. It is not onto because here this z has no corresponding what's this x in x. So this is not onto. So This is not on 2. Alright, so this is how we look at this on 2 functions, and this wraps up the introduction to these functions.